let's talk about a couple examples quickly here with the concept of time dilation. So we have an example. A rocket ship leaves Earth traveling at a constant speed of 0.5 c, so half the speed of light, towards Alpha Centauri 4 light years away. The journey takes 8 years from the Earth's frame of reference. How long does it take from a frame of reference on the ship? So we have the ship traveling, and then we have Earth, and we have Alpha Centauri. Alpha Centauri. Now, the problem is we need to figure out what our proper values are, because unlike with physics problems before where we just throw some things up, now we have different sets of time intervals, we have different sets of distances, you'll see, and all of that. So this is sort of what we want to think about, is what is our proper frame of reference in this case? Well, our events are the spaceship being at the same position as Earth, and the event of the spaceship being at the same position as Alpha Centauri. So the frame of reference needs to be one that's not moving relative to Earth and not moving relative to Alpha Centauri. So that would be, say, either the frame of reference of being on Earth or of being on Alpha Centauri. And in both of those cases, we know that this distance, the delta x proper interval of distance, is equal to 4 light years. Because we said this is assumed to be in the proper interval because it's the measurement we're going to take from Earth to Alpha Centauri. Okay? And then we know that also that means that on Earth or on Alpha Centauri, that's what we want for our proper time, which they tell us right here. 8 years from the Earth's frame of reference, which we know is the proper in this case. So we have this, and then we have the speed of the rocket ship is 0.5 c. And we're asked on the rocket ship, what is how much time passes? So on the rocket ship, how much time passes? What's our observed time on the rocket ship? So this is different than what you saw in the previous video where proper time was on the rocket ship, and that's because we were starting with the clock on the rocket ship. In this case, we're starting with the clock on Earth. So that's why we're doing it differently, because we're starting from the reference frame of the Earth to Alpha Centauri. That's what we know about, and that's the thing that's not moving. The starting and ending positions aren't moving relative to the reference frame. So jumping into that, let's first solve for gamma because it'll be easier to kind of work with here. So this is 1 over the square root of 1 minus 0.5 squared, 5c squared over c squared. And now you'll see where it's nice when we report these in terms of c, because this c squared cancels with this c squared, and we just get 1 over square root of 1 minus 0.25, which means we get 1 over square root of 0.75. We'll have to plug that into a calculator real quick. Square root 0.75 is 0.866, so 1 divided by we get 1.15, yeah. And you'll notice gamma doesn't have any units because the units of meters per second on C cancel with the units of meters per second on this C because they're both squared. So they both have meters squared per second squared that cancel. So our gamma is 1.15, and if you remember, delta t, observed time, is equal to gamma times the proper time. And I'm realizing I've done this backwards. Oh, yeah, sorry. This is because we want to find the time that's passed on this clock. So this is the proper time. Because it's in the frame of reference of the traveling. And this delta t should be 8 years. So it should actually be 8 is equal to gamma times the 1.15 by 8 years, gamma. So then we divide 8 by 1.15. And we get 6.96. Sorry, that's not right. It should be 1.15 delta t naught. So that means delta t naught is 6.96 years. And so what we see is time is moving slower. Less time passes on the spaceship. It's only about 7 years as opposed to 8. So another example, a friend of yours is riding a rocket ship traveling at point 9c. They send a message every year in their frame of reference to update you on their progress from your frame of reference, how long passes between each of these transmissions. So let's first calculate our gamma, just so that's out of the way. So that's 1 over the square root of 1 minus 0.9c squared over c squared. So 0.9c that will give us 0 square root so if we calculate all that, we get a gamma factor of 2.29. So this is the gamma between a rocket ship and a frame of reference of the Earth. So they're sending the message, so proper time is on the ship. So delta t naught is equal to 0, or sorry, is equal to 1. Because that's on the rocket ship. That's where the transmissions are being sent from. So that's kind of where we're having our events occur. And then we're on Earth observing those or receiving those. So delta t equals 2.29 times delta t naught. So delta t is equal to, if t naught is 1, 2.29 years. So on Earth, you're going to observe that they send those messages. Those messages are being sent out every 2.29 years. Okay, I want to introduce two paradoxes, and then we'll talk about those in our time together. So Alice and Bob are on spaceships traveling in opposite directions. From Alice's perspective, time is dilated on Bob's ship. From Bob's perspective, time is dilated on Alice's ship. And so this is true. This is a true statement. So in both cases, both Alice and Bob think that they are not moving. And when they look at the other ship, it looks like the other ship is moving away from them. So in both their cases, they see from their stationary reference frame a moving reference frame. And assume that time is dilated in that moving reference frame. So the question is, who is right? How much time actually passes? So if they're both thinking that the other person's time is dilated, who is right? Like, which of them is right? And how do we know how much time actually passes between events? So the second question question is a bit longer that takes some explanation. But that first one you can think about, maybe bring some thoughts to class. Imagine there's a 2-to-1 time dilation factor. So we're saying basically gamma is equal to 2. So time passes half as fast for the moving reference frame. Alice and Bob both leave at time 0. Alice records a journal and sends it to the Bob at the end of the first year. So she knows this means that only 6 months has passed for Bob, because again, she sees Bob moving away from her. And so she thinks, oh, time is moving slower on Bob's ship. So after 6 months, or after a year for me, it's only going to be 6 months for Bob. So she sends off her journal. So then we're saying, if this means that Bob receives this message after that 6 months, he's going to think, well, I got a message from Alice. She's moving, so time is dilated for her. So she's only been, traveling for 3 months. So he's going to, so in this case, he assumes that, only 3 months have passed for Alice. So then he sends that journal back to Alice. And then does this mean that when it gets to Alice, she'll receive it after 3 months, and essentially back in time in this case? So there's a bunch of assumptions in there, and you can go back and re-listen to it if you want. And you need to either figure out, A, this is true, why that makes sense, or B, this is not true, and which of those assumptions, if any, were incorrect. So you can jump into that and let me know if you have any questions. Otherwise, we'll talk about these in class together.